Right. See, amines is another small topic. So, what all things we need to learn? Let's see one by one. First thing is about IUPAC name and nomenclature. So, if you have CH3NH2, it's a 1-degree amine, and IUPAC name is methanamine. And here it is a 2-degree amine, and IUPAC name is N-methyl ethanamine. Okay, and these are 3-degree amines. In case if you have NH2 on benzene, we can call it as benzene amine, aniline, or aminobenzene. So all these are accepted IUPAC names. If you have a CH3 along with NH2, we call it as O-toluidine. If it is at ortho position, it is O-toluidine, and so on. Okay. And next, in case if you have it at para position, then it will be paratoluidine and so on. So next, check. If you have two NH2 groups, we call it as O-phenylene diamine. Okay. And if you have NH2 on this carbon, so the common name is benzylamine. The IUPAC name is phenyl methanamine. As a three-membered rings, as a ring which is heterocyclic, if it is a three-membered ring, we call it as aziridine, accepted IUPAC. If it is four-membered, azitidine, five-membered, pyrrolidine, six-membered, piperidine. And if the pyrrolidine is converted into an aromatic ring, it is called pyrrole. If piperidine is converted into an aromatic ring, it is called pyridine. And if the pyrrole is further converted into N substitution here, so that will become imidazole. If you have a three-membered, if you have a bicyclo nitrogen group, that is quinacridine. And if you have same kind of quinacridine with two nitrogens, it is called diazobicyclooctane. Okay, DAPCO, diazobicyclooctane. This is quinoline. Okay. Now, these are ones which are very, very important. Okay, going ahead, I think you should also learn this pyrrolidine as well as piperidine while solving questions, especially in the case of cyclic structures. All right. This is typically how the uh, nomenclature works for amines. The next important part is how do we identify the isomers of various amines? For example, if you have C4H11N, so let us see what are all the isomers which are present in it. Check out always the degree of unsaturation. Degree of unsaturation is number of carbons plus 1 minus number of hydrogens minus number of nitrogens by 2. Okay, so that includes 5 minus 11 minus 1 by 2. Right, so 5 minus 5 is 0. So there is no double bond, it is a straight chain. So since it is DOU1 or DOU0, so I can write this as 4 carbons 1, 2, 3, 4 with NH2. That is 1 degree amine. Then I can put 1 degree amine here also. And I can put 1 degree amine like this also, which a branched form. And I can put 1 degree amine like this also. So these are the 4 1 degree amines. Then I can have a 2 degree amine like this NH and like this. And I can keep a 2 degree amine this way also with a methyl substitution. And I can keep a 2 degree amine with an isopropyl also like this. And finally, I can have 1 3 degree amine like this. These are all, sorry, one more ethyl. These are all the isomers we can see. So let me mark them. So this is 1 degree, 1 degree, 1 degree, and 1 degree, 2 degree, 2 degree, 2 degree, and 3 degree. Okay. There are certain important pointers that we need to note it from this question. First, 1 degree, 2 degree, 3 degree are okay are functional isomers. Functional isomers. Got it? So they are not some positional also. It is always functional isomers. Next, let me label this one also. So that is, this is structure 1, 2, 3, 4, 5, 6, 7, and 8. Now, The second point that we need to note here is, if you notice the fifth structure and sixth structure, they are both 2 degree, but they are differing only by the length, chain length here, as well as the number of methyl groups on left hand side and right hand side. Therefore, because the functional group is same, I can say 5, 6. These two are 5 and 6 are metamers. 5 and 6 are metamers. Correct. And likewise, I can say 6 and 7. Now the chain length is same, only the position is changing. So 6 and 7 are positional isomers. Positional isomers. Okay. Next, if you notice the second one is chiral carbon. This is a chiral center. So second one is chiral. So this will have two stereoisomers, two stereo, and both of them are resolvable because they are chiral centers which are enantiomers of each other, so they are resolvable. Second, if you may have noticed, even when it comes to this position, this 2 degree and this 2 degree, that is 6 and 7, 6 and 7, both of them also show, you know, this is also showing chirality, this is also showing chirality with respect to nitrogen. Correct. So both has chiral centers, chiral centers at nitrogen, but non-resolvable, non-resolvable. Okay, so we can call this as, okay, chirally non-resolvable form, which means they might appear like chiral and they might rotate the plane polarized light, but the problem is you cannot isolate them. Okay, because of the umbrella inversion or because of the amine inversion. So both will show something called amine inversion. Due to amine inversion, they will interconvert into interconvert into enantiomers very easily. Hence, we cannot separate them out. So since we can't separate them out, we call them as non-resolvable. Okay. So multiple questions have been asked from this formula. That is, for this formula, which of them are, how many are chiral molecules? So answer is 2. And how many of them are resolvable? 2. How many of them are non-resolvable chiral molecules, which is 6 and 7? These two are the ones. So like this, any questions can be asked, you should be ready for it. Okay, guys. Right. See the next one. How many benzenoid amines with molecular formula given? So C7H9N. So how many benzenoid formulas we can make out of it? So let's see, we can make how many benzene forms here. So based on benzene here and DOU, if you notice, let me calculate the DOU here. So this is 8 minus 8 by 2. So 4, which means other than benzene, we cannot have any other double bonds and so. So I can keep NH2 here. I can keep NH2 here and put one methyl group here like this, CH3, which will go at ortho, meta and para. So this is one. And I can keep methyl here and then I can keep NH2 here. So that is one compound. Or I can keep NH at the center and put CH3 here. So that is another one. So total we got here as 5. So total 5 isomers. Okay. These are the benzenoid forms. Correct. Now, suppose if at all the question is asked out of this, how many benzene derivatives are present? How many? How many benzene derivatives? Which means here we need to consider benzene present with NH2, because now this is an aniline which is based on a benzene derivative. Now, if this is CH2NH2, this is an alkyl derivative. So in that case, these three plus one, you will count it as four. So four benzene derivatives here. Correct? And how many alkyl derivatives? Alkyl derivatives. One. So one alkyl derivative. So remember the terminology. This has been asked in JEE mains, right? How many benzene derivatives of the following? So a lot of kids made it wrong as five. Okay. So because this is connected to alkyl group, so this cannot be counted as benzene derivative. Okay. Now the next part of amines is about preparation, especially from nitro compounds. So in case if you have nitro benzene, if you treat with H2 by palladium, nickel, and all of these cases, we can directly get a benzene here like this, reduced into NH2. So this will get reduced into NH2. And tin and HCl, iron and HCl, both would give us aniline, I mean NH2, NH2 only. Correct? So what you need to know is that uh, tin in HCl, tin in HCl is preferred over SN in HCl, okay, as FeCl3 formed, can easily hydrolyze, to FeOH twice plus HCl, okay. Hence, small amount, of HCl is enough. All right. So that's why it can reduce more rapidly compared to that of SnHCl. Okay. Typically, you got to understand how does this reduction works. That in case if you have aniline and I'm treating with any peroxy acids, or any peroxy groups, it will convert into nitro. That means it gets oxidized to nitro. And if at all I reduce it by acid, mineral acid in HCl, it will get reduced, sorry, metal in a mineral acid, it will reduce into NH2. Okay. This is how the interconversion takes place. Next, if you have nitrobenzene here and you are treating with lithium aluminum hydride, so the reduction would go like this with N double bond N, and we shall have this as azo group. Okay. So this azo group is called as azobenzene. Now this is very unlike lithium aluminum hydride, correct? Because normally when it comes to lithium aluminum hydride, it is always expected to reduce up to amines, but not in the case of benzene. In the case of benzene, after it forms azobenzene, further reduction is not observed or breaking of bond is not observed. Got it? Next. If you have nitrobenzene with acids, mineral acid, no doubt, every mineral acid will produce into NH2 here. So there is no problem here. But instead of mineral acid, if at all I take a neutral solution with zinc will only stop at uh, hydroxylamine like this. It will stop at hydroxylamine. Okay. And in the case of base, if you have a medium, so in case of basic medium, first it forms an azo, and that azo will also get reduced to NH here like this. So this is like an azo group with two hydrogens. So that's why it is called as hydrazobenzene. It is termed as hydrazobenzene. Okay, clear? This is how it will take place. Now, as a sequence, if at all I tell you what is happening, in the overall reactions, let me tell you in generally what is happening here is that whenever you have NO2 here, NO2, correct? So first you will start getting two nascent hydrogens here. Okay. So that is N, H, and O, H, and another one will be like OH here, correct, with plus, correct. Sorry, O minus here, O minus, plus and minus. Okay, because the structurally nitro is double bond O and O minus and plus like this. So imagine as if I've added two nascent hydrogens to this base. Okay, so as we add nascent hydrogens to this one, so the next part is about removing out this OH here. Okay, so that means this double bond will come and OH will go away. Correct. So then we will first get this into N double bond O. So basically it is like this. This H will transfer here and remove it as OH2. So that will give you nitroso. And nitroso, if you react with, that means I'm adding how many nascent hydrogens? I've added two nascent hydrogens. Again, if at all I add two nascent hydrogens, it will go all the way to hydroxyl amine, that is NH and OH. Okay. And if I add another two nascent hydrogens here, it will go up to, you know, NH2 and OH2 like this. So it gets separated out. Okay. So which clearly suggests that in case if at all I want to reduce nitro to aniline, nitro to aniline, so we would probably require six nascent hydrogens. Six nascent hydrogen is nothing but six electrons, which means for reduction of nitro to aniline, we require six electrons. Got it? So while solving questions also, we need to remember that how much is the oxidation state or how much is the difference in the electrons between oxidized part and reduced part. Okay. Now, unlike this, what happened when it comes to these cases, right? When it comes to lithium aluminum hydride or when it comes to zinc in sodium NaOH, these cases probably what is happening. This is only a guess. Okay, there is no mechanism given as such, so it is only a guess that probably something like an hyd NH and OH which we have made, NH, OH, and H which we have made here like this. In case if at all we treat this with uh, uh, O double bond N, another reduced form. Let's say another reduced form here. So probably first a protonation is, first and removal of water is happening like this. So after removal of water, it will go through reduction as N, okay, with O here, and then nitrogen, double bond nitrogen, and this one, correct. This is a compound that might be formed, correct. So this is called azoxybenzene. Azoxybenzene. Imagine reducing this azoxybenzene two times. Removing that with water here. So we'll get this as OH2 here. So another two nascent hydrogens if you add. So probably that will be removed out and it will get into N double bond N with this benzene. So this will become azobenzene. Azobenzene. And if this gets further reduced with two more nascent hydrogens, so we will get this as hydrazobenzene. NH, NH, and then we have this benzene. This is hydraz, hydrazo, hydrazobenzene. Okay. So I guess you understood that, you know, why instead of simply getting aniline, we might get these multiple products in different cases. Okay. The reason is there could be an inter attack of molecules which might be more reduced and which might be less reduced, and both can come together to form these kind of products as oxybenzene, azobenzene, or hydroxybenzene. So we don't know way to control it, so we just need to know the end result. So the end result is like this. In the case of lithium aluminum hydride, you will remember strongly that it will end up at azobenzene. In the case of zinc and NaOH, you will remember strongly that it will end up hydrazobenzene. Clear, guys? Have you got an idea what is happening here? Okay. So I would want you to please check out once quickly. If you want to, if you already have the notes, please make a note of it. Quick. Right. The next part, what I'm putting is like the exceptions you need to understand. As in, now earlier how I put is in terms of hydrides, right? How the hydrides are moving. Now I'll put in terms of electrolytic reduction. The same thing I'm writing it again, but this time I'm putting it in as electrolytic reduction. That means how many number of electrons that we are giving towards the nitrobenzene. Okay. For example, if you have PHN, okay, starting with NO2 here, so which is double bond O and O minus and plus. This is how the nitrobenzene is. And imagine the first electron which we are giving, correct, is towards nitrogen because that has an positive charge on it. So that makes it N here. And it will push away electrons towards oxygen. So we'll get this as O minus and O minus. And then we are adding one more electron to it. Okay. So that will become a pair now. So now it will become a pair with O minus and O minus. Agreed? And now imagine as if you are pushing some acidic solution. And that's what we are doing, right? We are adding some we are adding some neutral solution which has polarized hydrogen, or we have acidic hydrogen. So in that case, what will happen is PHN with a lone pair here, and then we will get this as O minus and OH. Okay, correct. So now it would be like NO is pushing it inside and OH is been relieving. Okay, so in that case, we will get this as PHN double bond O. Okay, up to this, I hope all of you got that. Now, once you get this nitroso, from nitro, we got up to nitroso. This is called nitrosobenzene. So from nitrosobenzene, again, imagine I pushing two electrons, right? So in that case, we'll get this as N, and with lone pair and lone pair getting a negative charge on it, and O minus will be present. And now pushing two H plus, that will be converting into PH, NH, and OH. So that's how we can get a hydroxylamine. Okay. And hydroxylamine, in case if I push further H plus, we'll get PH, NH, and OH2 plus. Okay. And OH2 plus is a good leaving group. And to that, if you add another two electrons, so water would be out here and NH will get negative charge plus H2. Correct. And that if at all I push H plus here, and we will get this as PHNH2. Okay. So again, you count the number of electrons, everybody. I'll put two different colors here. Check first color is electrons. 1, 2. Then I post 2 here and 2 here. Total 6. Check out how many hydrogens, how many H plus I have used. 1 and 2, 3 and 1, 4. And then we have how many I used? 4. And then I have used this as 5. Correct. Now basically one more H2O, one more H plus will make it into NH3 plus, and that water will take it away. So I'm not pushing into that part. So it is all about number of electrons that we need to know. Correct. Now what are all the important bases what I can say from electrolytic reduction is that in case if you find, see this, in case if you find uh, nitro, correct, and then you are pushing for electrolytic reduction, right, in weakly acidic medium. It is in weakly acidic medium, still you will end up getting as aniline. The reaction might be slow, but you'll end up getting aniline. Okay. Now if you have strong, suppose if you have electrolytic reduction in strong acidic medium, strong acidic medium, correct, first it might get into this NH2 part here. First you'll get this NH. While getting this as NH, first you'll get OH, and I mean the H which is present here, correct? This can undergo rearrangement also, which means what you would notice here is this hydrogen can come here and OH can come at this position. This is called, Hoffman, Hoffman, okay, uh, Maritus rearrangement. Hoffman Maritus rearrangement. If that happens, you would see we will get this as NH2 here and OH here, like this. So usually in the case of strong acidic cases, we might end up here as well. Got it? Okay. So in case if you have it in an alkaline medium, okay. So suppose if you have ER happening in alkaline medium, what is happening in alkaline medium, we might end up getting this hydrazo, that is NH, and pH. What is this one? Hydrazobenzene. Got it? Right? And other cases, the little more random cases, what we have seen, random cases which we have noticed is that in case if you have nitro, correct, and imagine treating this with CH3O minus, correct, Na plus with CH3OH, got it, and followed by glucose, that means in the presence of glucose and NaOH, got it. This would give you hydrazo. I mean, no mechanism here. Yes, said only forms we should know. So this is azoxybenzene. Azoxybenzene. Okay. Likewise, if I take another case here where we are using uh, alkaline sodium, sorry, like this, alkaline, okay, sodium stannate, that is Na2SNO2. That will also give you pH and double bond N and pH, or lithium aluminum hydride, any one of that. Got it? And in case if at all I use this as I think in sodium also, sorry, I forgot to mention the zinc also, or zinc. Zinc in NaOH, zinc in NaOH, correct, with CH3OH. CH3OH if you have. So this will control, CH3OH will control, and it does not make this to convert into hydrazo. So it will stop at this position only. Got it? Right. So these are the cases which you need to know elsewhere. Okay. And you might get an idea about how the electrolytic reduction is actually happening. Okay. So please check. This page I missed out in my pre-notes. So please, if possible, once I share with the complete notes, I would suggest you please go through it once. Okay. Right. Now I can say this as overall reaction. If you have zinc and this, or zinc in NaOH, and here this is not the one, just sorry, this is not the one, zinc in NaOH. So this we just learned it as pH, N double bond N and pH. Okay. While if you have a simple nitros, alkyl nitros, every alkyl nitro on reduction, whether it is SnHCl, FeHCl, nickel, lithium aluminum hydride, zinc in HCl, correct? Or even if you have zinc in NaOH, correct? All of these would convert that into amines only, simple amines. Here there is no such distinction. The problem comes only when you have it on a benzene form. Right, everybody? This is how the reaction will take place. Now see, this is very very interesting. Second one is selective reduction. Okay, so when do we get to see something called selective reduction? Selective reduction is when you have multiple NO2 groups and you are only trying to reduce one of it. Okay, this is possible when you use aqueous Na2SO4. This is all aqueous Na2S, aqueous ammonium sulfide, or aqueous ammonium sulfite with a double, I mean, SS linkage. Okay, peroxysulfate kind of a thing. Or you can simply have this one with water or NH4HS. All of these reagents will give you the same thing. The product is like this. So basically, we will have one part of the nitro getting reduced into NH2, one part of the nitro will remain. And this will usually happen as 3 moles of ammonia plus 3 moles of sulfur. In case I'm assuming that I'm treating that with ammonium sulfide. So in that case, with 2 moles and 2 moles of H2. This is with ammonium sulfide. Okay, like this you can get it with other molecules also. Got it? All okay. Now this would work even when you have 3 NO2 groups also, everybody. That is, in case if you have, you know, NO2 group here, NO2 here, and NO2 here, like this. And that is being used for, reduction with ammonium sulfide like this. Okay, in aqueous medium. So in that case, we will get one of them getting reduced as NH2 and other two will remain as nitro. So it also often observed in with two. There is no mechanism as such. We just need to remember it. What is happening in this case? That's all. All right. What if I now react with, H2 and nickel? H2 and nickel will be readily reducing all the nitro forms, correct, into NH2. So this will become NH2, NH2, and NH2. And I'm just continuing that. What if I react with, HNO2 in excess? HNO2 is a disonium salt, correct? And that followed by warm water, H2O, warm water, right? H2O warm. So that means it will be converting everything into H, sorry, OH, 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 and OH. This is what you'll get. So this kind of questions can be asked. First, you make it a selective reduction and then followed. Most of the questions will be like this, where you have selective reduction done that has been followed up with HNO2. HNO2 will convert into disonium salt. From disonium salt, we have a lot of reactions. I hope you guys are clear with the idea. Right. Let us quickly go through some questions based on whatever we have studied in the first 5 6 chapters, right, from hydrocarbons to alkyl halides to alcohols to aldehydes, ketones, right, carboxylic acid. All that application, all that together now becomes very easier to assess the sequential reactions. Got it? So let me uh, let me show you how to solve this. At the same time, I want all of you to do it together. Okay, I request you, all of you, to do it together on your books. If you do not have the printout also, please write this as a question and then start working it out. All right? Because all these sequential reactions will keep on reminding you what happened in the previous topics. You'll be able to recall that quickly. Okay? So, right? Check out first question. So we have a nitro reacting with H2 and nickel. So what is the A that we expect? A is definitely amine. And then B is about exhaustive methylation. So you are making all the methyl groups to connect. So I'll have N, N, N with plus, and I have this as minus, I minus part. Got it? And then In case if at all I use something like ETO minus here, correct? So then I would be able to make an elimination here via E2. And E2 elimination while making here, you will get this is alpha and beta and beta. Usually, NR3 is a very bad leaving group, so it will favor Hoffman products. Hence, compound C will be and Hoffman product. So, which means I'll get a double bond here plus N trimethyl here. So, instead of taking this, usually we always take Ag2O moist and heat. Okay. Ag2O moist will make this Ag will make this iodides to get precipitated as AgI, and oxide will convert into OH minus, which will act like a base to make the elimination happen. Okay. So this last reaction from B to C is also called as exhaustive Hoffman elimination. Okay. All of you are done. This is an important recall from the previous topics. Okay. Right. Now notice next one. You're reacting with AgNO2 with Ag in the presence of bromine. So that will help us easily to make AgBr precipitate. Okay. First you'll get AgBr precipitate and NO2 minus will attach here. So what is A here now? A will be NO2 and the attack will be from the nitrogen end. Okay. Not from the oxygen end, but it will be from nitrogen end. If it is KNO2, the attack will be from the oxygen end. So next, B is about reduction. So we'll be able to reduce this into NH2. And thereafter, again, C is exhaustive Hoffman elimination. So that makes it nitrogen with methyl, methyl, methyl with plus charge. And D is about the elimination part. So elimination will be double bond plus NME thrice. Okay. So remember, this we have learned in alkyl halides. This we have learned in alcohols. This we have learned earlier in alkenes. Okay. This entire thing we learn it as alkenes. So make a quick recall, everybody. First word, see the next one. Okay, if you have not written, just write it with me, along with me. So first we have, write down 3 moles of acetylene. 3 moles of acetylene with red hot iron copper tube. What do we get? Red hot copper tube will generate benzene. Okay. Then continue writing this arrow. What will you get? Concentrated HNO3 that will make it into nitrobenzene. This is a nitration step. And then C, we just learned it. Iron in HCl will give you aniline. We'll get this as NH2, right? Then D, what does D does here? DCH3COCl, basically it will get the lone pair from here will attack here and remove this Cl. So amide formation will happen. Okay, so we will get this as NH C double bond of CH3. Very, very important compound for our reactions. Okay. What do we call this? This is called, because an acetyl group is present, common name is acetanilide. Acetanilide. Okay. So acetanilide formation is observed, right? Thereafter, you are making a reduction with lithium aluminum hydride. That will reduce this into amines. So NHCH2CH3. So it will form a secondary amine. And then again I'm doing exhaustive methylation. So that makes it NH, so that H will go away. I'll get methyl, methyl and CH2, CH3 with a plus charge, right? This is F, of course, with minus also here. This one is F. And G is again elimination. On elimination, what do I get? With this benzene and N, Me twice. This will remain plus I will get this as CH2 double bond CH2. So that is our compound G. So this is our compound G, alkene. Very important sequence. Please check and learn. Everybody try to recall it. And this is a time to, check whether your organic is, getting better or not. Okay. Just a minute. Sorry. Right. Third one is done, everybody. Chalo. Let's see the fourth one now. Chalo. What is A here? N2O5 in acid anhydrate will always give you, nitrobenzene. So we will get this as nitrobenzene, NO2. Okay. Then what is B? Again, you are making a again you are making a nitration. So because NO2 is a meta directing, you will get this at meta position. When you have two NO2 and Na2S is used, you will get a partial reduction. So that makes it one of them to convert into NH2. And D is about acetylation. Just now we have done. So we will get this as NO2. And here you will get this as NH. C double bond O CH3. So this is acetanilide with nitro substitution. And D then E. E is about reduction. So reduction will happen at NH2. Okay. Amides usually does not get easily reduced. So I'm not counting that amides will get reduced in this case. Okay. Then E. Then check out what will happen with F. F is about reaction with HNO2. HNO2 reaction will give you disonium salt. N2 plus and Cl minus. Here NH C double bond O CH3 is still present as the same thing. And then G is about disonium salt converting into bromine here using Sandmeyer reaction. I'm sure you guys can recall that. It is Sandmeyer's reaction. We studied in alkyl halides, aryl halides. Next, what is H? H is about removing this, hydrolyzing this again. Amides on hydrolysis. We learned in carboxylic acid that amides can get hydrolyzed and that will give you NH2 and CH3COOH. Okay, CH3CO minus because it is in basic medium. So this is the H part that you need to report. Please check. Finished. Right. See the fifth sequence now. Check out the fifth sequence, everybody. So keep writing simultaneously. Check out. First we have nitro. Write the nitro part. Tin with HCl. What do we first get? We will get amine B. And amine, when you react with NaNH2 aqueous and HCl, it is HNO2. That will become disonium salt. But disonium salt is extremely unstable in an alkyl form. It is only stable in aryl form. So here it will hydrolyze easily to convert into alcohol. So you will report only alcohol. And alcohol when you react with concentrated H2SO4, we learned that it will convert into an alkene. And alkene, when you make an nucleo electrophilic addition, you'll get two bromines here. Okay. Next E, when you use NaNH2 and excess, it will give you elimination, which is C minus Na plus, because you are using excess. And F, when you use Tollens reagent will actually make this minus and silver plus into a precipitate form, a white pipitase form. Okay, so this is another important sequence. Check. Finished? Right. All right. These are some important reactions that you need to remember. I'm leaving some space in case if we recall one more important sequence somewhere, we can write it again. Now let's go to the second reaction of preparation of amines. This is a very interesting one. Gabriel thalamide synthesis. Okay, GPS. Remember it like GPS. Gabriel thalamide synthesis. Gabriel thalamide synthesis is specifically designed for making primary amines. If you want to get primary amines from the reactants, then Gabriel thalamide synthesis is used. Check how. First, we need to generate something called thalamide. This is thalamide. Okay. So that is, it is derived from phthalic acid. And as you react with excess amount of ammonia, strong heating, you will get this as thalamide. Imide is when you have two amide connections, you call it as imide. And that when you react with KOH, OH minus will take this H plus because this hydrogen is sufficiently acidic, and you'll get minus. That minus will attack R to remove this X here. So you will get this as N-alkyl thalamide. So we'll get this as N-alkyl thalamide. And then when you react with OH minus, it will attack on this position here. So it will attack on this position here. It will open up the bond here. So we will get one side an acid, another side we have NH. So obviously this N minus will take this H plus and convert that into amide, and the other side we have an acidic form. If you react with the second mole of OH minus, that will also attack here. It will break here, and you will get this as an acid and NH minus. NH minus can definitely take H plus from the aqueous solution and convert that into primary amine, while this will also take H plus and convert itself into phthalic acid. So you will get a 1 degree amine and a phthalic acid. Both can be easily separated or based on their boiling points. Distillation can be done, and you can nicely remove out this primary amine. Okay. Alternative method is that you take once you have some alkyl substitution here up to this N-alkyl thalamide, the step is the same. After that, in case if you react with hydrazine instead of reacting in KOH, suppose if we react this with in hydrazine, so hydrazine will go attack here, second nitrogen will attack here, then both will remove out nitrogen in the form of RNH2. Okay. So this would be a better deal because here removing NH2 minus is very difficult. You require some heat also. So while here it can be much easier. First, it will form a very nice cyclic ring, which is hydrathalimide. So, and RNH2 as a primary amine can be extracted. Another way here, basically, we are checking the application of this GPS, okay, Gabriel Thalamide synthesis. You know that in basic medium, we can get it as N minus, right? So you get this as N minus. Now, what if you have alpha halo ester? This is an alpha halo ester. So N minus can attack strongly here to remove Cl minus because there is a withdrawing group. It will highly favor SN2 mechanism. So as it attacks, Cl minus is relieved, you will get this compound. And now you hydrolyze it. On hydrolysis, first esters will get hydrolyzed, you will get acids. Further hydrolysis, this entire amide will get hydrolyzed and you'll get alpha amino acid. That's a very important starting point for making proteins or amino acids. So if you want to make amino acids, this is the best way to prepare. Okay, this is about making amino acids, everybody. Clear? Please go through it once quickly. What is Gabriel Thalamide synthesis? Let's see what are the alternate methods for preparation of anilines. If you have chlorobenzene and react with ammonia and heat, you will not get any product. But if the same thing is done in the presence of Cu2O, in that case, this will act, it will become a very strong base in the presence of Cu2O as it becomes NH2 minus, and that will make an benzene mechanism through benzene mechanism like this. You will get this as a triple bond here, benzene form, and that benzene form as it reacts with NH3 finally give you aniline. Okay, that will give you aniline. Got it? Next. This is a typical benzene mechanism. Usually happens at very low temperature. So that will also offer you NH2. Okay. In case if you have any withdrawing groups like NO2 and NO2 are the withdrawing groups here. So then we can also get this as NH2 here with NO2 and NO2. So which type of mechanism? ARSN2. ARSN2 type of mechanism. Here it is benzene mechanism. Benzene mechanism. And the same follows here also. Okay. In case if you have CH2NH2, so it will become a secondary amine NHCH3 with NO2 and NO2. These are the type of reactions. Again, ARSN2 type of reaction here. So this is one way to start substituting NH2 group or making more into amine forms on benzene. Next, what if you want to get simple amines? Okay, other than Gabriel Thalamide synthesis, which is the best way. Of course, Hoffman ammonolysis is another way, but here this is not as good as that of Gabriel Thalamide synthesis. Why? Because see, in this reaction, if you take an alkyl halide, you have to react with ammonia to remove this X via SN2 mechanism. So first you will get NH2, and if you have RX present, in a larger quantity, that ammonia would again attack, remove this X, so you'll get a secondary amine. If you keep doing that further, you'll get tertiary and eventually quaternary. So basically, you're not getting one as a major product. You'll get 1 degree, 2 degree, 3 degree, 4 degree. You'll have a mixture of four, mixture of all four. Okay. But certainly we can say that if Rx is excess, so majority part will be stopping at this point. So I can say that if Rx is excess, Rx is excess, okay, then quaternary ammonium salt. This is quaternary ammonium salt. Quaternary ammonium salt is major. That is major. But if ammonia, if NH3 is in excess, is excess. Then 1 degree amine RNH2 is major. Okay, but still it's not as major as that of 90-10 percentage. You still have a large quantity of 2 degree, 3 degree and quaternary ammonium salt. All okay, everybody? This is how the reaction favors in Hoffman ammonolysis. Okay, Hoffman ammonolysis is quite reversible. That means if you have Rx plus NH3, we are expecting that this will form as RNH2, correct? Plus HX. But this HX can again protonate this and make the X minus attack once again, correct? So if you want this to be less reversible, I want to make sure that this HX is removed out. So what I can do, I can use ammonia in the presence of pyridine. So if I use some pyridine here, okay, so using some pyridine, we'll convert this into RNH2, and here the pyridinium chloride or pyridinium halogen will be formed. So that will avoid a backward reaction here. Okay, this is Hoffman ammonolysis. Here, everybody, this is how the preparation of amines can be done. Okay, next, in case if you directly react with ammonia, okay, if you're directly reacting with ammonia, but you have tertiary amine. Tertiary amine will always lead to the formation of alkenes via E2 mechanism. So you'll get this as NH3 plus HCl, and this is via E2 mechanism. So this will be major. Internally, if you have nitrogen, it can attack internally and remove bromine. So that is also via SN2. I mean, neighboring group participation. You will get NH. So here I can say this is an NGP type of mechanism, neighboring group participation. So what are we getting? This is aziridine, three-membered ring. Same thing. First, I can attack NH2. I mean, first NH2 can be attacked here, remove NH2, and internally again from here it can attach on this position. So we will get this as a five-membered ring here with N like this with methyl. So this is the reaction that will happen. And if you react with NaN3, that is if you have Rx and I react this with NaN3, this is an SN2 mechanism where first I'll get this as Rn3 as the product here, and then if you react this with lithium aluminum hydride, it will convert into RNH2 plus N2. See how is that possible? Check R N triple bond N plus and minus. This is how the structure is. Okay, so when you react with H minus, so this group will go away and that H will come on nitrogen. Okay, so that's how you will get this as RNH2 and NH2. Okay, now is it the only case? No, in fact you can utilize this by NaBH4 also. I mean, we can make this reaction through NaBH4 also, or you can make this reaction using B2H6 also. All of them will reduce into same amine forms. Got it? I hope this part is clear. Similarly, just like how we have, this azide form, the other alternative form which we can use here is, RCH or CR dash here and double bond N and OH. This is ketoxime. Ketoximes, when you react with a reducing agent, okay, that will also convert this into H and NH2. Okay. Well, what are all the reducing agent we can use? I can use lithium aluminum hydride for sure. Got it? I can use sodium in ethanol, Bowold blank reduction, and I can use nickel in H2. Got it? I can use NaBH thrice Cn. Okay, this can also be used. So all of them will make this into an. Another reaction which we can convert this into amines, right? Another such reaction here would be when you have cyanides, that is RC triple bond N, and that if at all we make a reduction to convert into RCH2 NH2. So we are trying to convert into an amine form. Okay. So which all reducing agent we can use in this case? It would be H2 plus either nickel, palladium, platinum with heat. This is one way, correct? Or we can use rannickel, got it? We can use lithium aluminum hydride. We can use sodium boron hydride. I mean, sodium in ethanol also. Sodium in ethanol. Okay. And lithium boron hydride, not sodium boron hydride, lithium boron hydride. B2H6 and THF. This can be used, correct? And any metal in acid, any metal in mineral acid like iron in HCl or tin in HCl and so on. These are all the reducing agent which can reduce these cyanides into amines. Can same follows for isocyanide also. Okay. And this is one famous reaction, that is when you have a cyanide and reacting with sodium in ethanol. Sodium in ethanol to convert this into RCH2 and NH2. This is called Mendius reduction. Mendius reduction. Okay. These are all various forms of uh, nitrogen connected groups which can be converted into amines. Okay. Yeah. Next. Check out the C part. C reaction is about amides. That is, if you have RC double bond O NH2 here, and if we perform some reducing, and if you make reductions, that also can be converted into RCH2 NH2. Now, in such case, what are all the reducing agents in this particular case? We will have BH3 with THF, BH3 in THF here. This is a excellent reducing agent out of all the forms. Sodium in ethanol, that is also a very good reducing agent. Next, lithium aluminum hydride. Okay. So what is to be avoided? Remember, avoid, you know, H2 by nickel. This will not perform so well with amides or rannickel or rannickel. In some books, they have given it like there is some reaction, but there is extremely conditional way. But in general, if you ask me the reactions, then the best reducing agents are these. Okay, these three can make that reduction happen. Okay, while if you have only imine, this as a note, correct? This is a note. It is only imine, that is CH double bond NH. This is an imine form. Imine. Imines are reduced by almost everybody. All reducing agents can easily reduce that into CH2 and NH2. Got it? We can take any reducing agent. That means all above mentioned reducing agent. Above mentioned reducing agents, they all can easily reduce, imines into amines. But only one case where we are not reducing, rather, we are easily going to be reversing this as well, which means if you react this in water or put it in water immediately, it will convert into aldehyde and ammonia. So avoid water, restall reducing agent will do this. So there should not be any contact in water, then the reaction will happen better. Okay. Finished. All we have done is all preparation of amines here. Now let's see what are all the chemical reactions and basic character or basic properties of amines. Starting with, whenever we have to discuss with base, so first we need to check out how easily it can accept H plus, convert into a conjugate base form. And if the Kb value for this is higher or pKb value is lower, then the basic strength is high. Or the alternative way of looking at it is if the conjugate acid is, stable. If it is stable, in that case the pK value will be higher. Or it is a weak acid. Stable means it is a weak acid. In that case, this will become a strong base as well. That means RNH2 is also a strong base. So this or more stable, like this. Stable conjugate acid. So either you check out these two properties, directly check out Kb value, or you check out the pKa value of the conjugate acid. So remember, most of the time we use these two cases only. Either the Kb value is high or not, or the pKb value of conjugate acid is high or not. If that means, amine is strong. So R NH2 is strong. Got it? This is what we need to know. Just a second. Done, everybody? Now, to increase the basic strength, everybody, what do we check? Either plus I plus m should be always increasing. I mean that higher the values of this plus m and plus m, that will increase the basic strength. And priority wise, first you give the hybridization as the priority. Check out hybridization. And if the nitrogen which is sp3 hybridized, that is usually going to have a uh, uh, higher basic strength compared to the one which has sp2 and the one which has sp. So you can notice this example here, nitrogen is sp3 hybridized, so that will be more basic than the one which is at sp2, the one which is sp hybridized. Okay, here you will not put any effects while you are comparing hybridization. You will not compare what all effects it has, whether it has plus m minus m, nothing. You will simply compare on the basis of hybridization. Second, the comparison is on the basis of localization, whether the electrons are delocalized or localized. For example, here electrons are delocalized, here electrons are localized. So the localized one will always be more basic. Third case, if the delocalized aromatic compounds are there, they are very, very least basic. That means this lone pair is delocalized, but that is becoming a part of an aromatic ring. So that means this will be extremely low basic compared to that of a normal sp2 nitrogen. Okay, this is an extremely low base, I mean weak base, while this is a very strong base. Okay, now in the case of aqueous solution, just try to recall from GOC what we learned, that solvation will always compete with inductive effect. Okay, that is, if you have ammonia, okay, ammonia does not offer any plus I. I mean, these hydrogens does not offer any plus I. While when you put it in water, what will happen? In the water, it will start becoming, after taking H plus, after taking H plus, it will start becoming like this plus, and here this side, this side, this side, and this side, we will have, you know, interaction with water, OH2, like this. Okay, clear? So this is how you'll have strong solvation. This is called solvation. Got it? Now, as you start increasing one alkyl group, if one alkyl group is increased, plus size is increasing, and solvation is decreasing now. So, because one end will be controlled by CH3, only three solvated molecules, solvated hydrogens will be observed. In case of 2 degree, now the plus size is increasing, but the solvation is again rapidly decreasing. By the time it comes to 3 degree, it will have very high plus I, but very low solvation. See, plus I and solvation both are going to stabilize both are going to increase the basic strength. Okay, but both of them are negating each other because when plus I increases, then solvation is decreasing. So, putting both the aspects together, what we can say, if the R group is methyl, right, in that case, 2 degree amine will be more basic, then 1 degree amine, then 3 degree amine, and then 0 degree amine. Okay, I mean ammonia. So 2130, remember the word, remember the numerical this way. 2130 is what you'll observe for uh, methyl. Similarly, when it comes to ethyl, you will observe this as 2310. So you'll observe this as 2310. Okay. Overall, what we need to learn it, this is an NCRT order. Please check it out. 2 degree amine will be the highest, then 3 degree, then 2 degree, uh, 2 degree uh, methyl group, and then we have 1 degree amine with an ethyl, then 1 degree amine with methyl, then 3 degree amine with ammonia, then we have PHCH2NH2, then we have ammonia. Then once you get ammonia, up to this, have you noticed everything is localized electrons? Up to this, everything is localized electrons. So thereafter, delocalization starts. Nitrogen is delocalized with benzene. Here it is delocalized, and here also it is delocalized. While it is having delocalized, it has two plus I groups. Here it has one plus I group. Here there is no plus I group. So this is the order we must remember, everybody. Okay, and this order is valid for aqueous solution only. All okay? Next, check out quickly how to compare the basic strength of these groups. So first we just learned it. Non-polar. Non-polar means in case of non-polar or gaseous medium, only plus I is the basis on which you will check out the basic strength. So on the cases of plus I can say C has most plus I, then B, then A, then D. This is the order of basic strength. Next, check out in gaseous state also it is the same. So C will be greater than B, then A, then D. Next, if you have this is delocalized, and this is localized. Since it is localized, D will be highest, then C, then B, then A. Okay. Next, this is completely sp hybridized. Here it is partially sp, this is sp2 hybridized. In fact, amides will have complete sp2 form here, and this one is partial sp2 to sp3. In fact, mostly sp3 kind. Here, because of resonance, it will have some loss of sp3 character. So mostly this is kind of sp3 case. So I can say C greater than B greater than A. Okay, got it? And what is the next one? Fifth one. This is completely localized. This is localized. This is highly delocalized. This is also delocalized. So first one is A, then C, then B. Okay. Here, this is localized. This is localized. But here in the bridge position, it will avoid any kind of inversion. So here in the case of nitrogen, it will always have some inversion. Inversion as in this nitrogen, will supposed to have like this ethyl, ethyl, and ethyl, making an pyramidal shape. But because of the amine inversion, so it will go through this kind of movement, this kind of planarity. So when it gains this planarity, it will start losing its basic character. Okay. So then after it getting the planarity, again it changes into, it will flip into this form. So because lone pair is flipping up and down, it is sometimes it will be shown up, sometimes it will be shown down. So its electron density is distributed. So therefore it will be less basic. While when it is already confined or it is restricted with the other molecules, then it is highly localized and available. So B will be more basic than A. And next one, in seventh one, you can see this one is donating, this one is donating. But here, from the other end, the nitrogen is withdrawing by inductive effect. So because of which we will say A is definitely more basic than B. A is more basic than B. Okay. Next, if you may remember, this is guanidine form. So these are guanidines. This is a guanidine. And guanidine is exceptionally strong base, correct? Because of its very, very stable conjugate acid. So these three are the conjugate acid pairs here. Let me show you how it is. So first imagine, I mean, this is the original molecule. This is the original molecule, how it is. Now, if at all it has to take H plus, it has to take here and this will become a plus charge. This is guanidine form. In that case, this lone pair can be pushed here, correct? And this pi bond can be shifted here. So in that case, what do I have here? So I will have, I mean, remove this double bond will come here, and this will be start gaining the plus charge. And in second case, if this lone pair, I mean, if this side the lone pair is pushed here like this, in that case, this will have lone pair, double bond will be here. This will start getting the plus charge now. It will start getting the plus charge, and here it will have NH2. So you can see 1, 2, and 3. All three are equivalent structures. Because they are equivalent structures, we can say this is a very strong base. Guanidine is very strong base. Okay. So because it is a strong base, wherever you have this system, guanidine system, they'll start showing more and more or stronger basic character. Check out the eighth case. This is completely localized. This is delocalized. Here, delocalize is not possible. Brett's rule. Here it is completely localized. And bridge positions will always have more basic strength. Then, if you compare between these two, this one and this one, here there is some withdrawing group, C double bond O. So A will be slightly better than C than B. Okay. This will be the basic character. Next, this is guanidine, this is amidine, and this is ammonia. So this is like half guanidine. Only half side will have resonance. Here will have resonance and all three sides here like this. So because of which guanidine is most basic form, and then amidine, and then ammonia. Okay. Next, if you have A, B, C, D here, just recall what is ortho effect from GOC. If you have any bulky group at the ortho position, the basic character of aniline drastically decreases. That is ortho effect. So now D is methyl is donating, which should actually increase the basic strength, and C will also increase. But instead of increasing at ortho position, it will drastically decrease. So that is why ortho will come out the end. Ortho will be at the last. Next, 11th, check out. We have A, B, C here. So now what happens when you have two methyl groups, right? In case of two methyl group, then SIR will be dominant. Since SIR is dominant here, we can say A is very strong base, then B, then C. SIR means steric inhibition of resonance. That is, if you have N methyl and methyl here, like this, sorry, this methyl and methyl will go out of the plane. They both will go out of the plane here, like this. When this methyl here and the other methyl is present here. Now, because it went out of the plane, now this lone pair which is present is in not conjugation with the pi bond. So here it will not be in conjugation. So therefore, now this lone pair is localized. So since it is localized, it will be acting like a strong base. This is SIR effect. Okay. Next, same thing. Here also SIR will help when you have NO2, NO2 and NO2. This NO2 will go out of the plane. So only minus I will act. And here in CH3, the plus I is acting. And here with cyanide, it is act because cyanide is linear. It does not have any SIR effect. It will show minus I also and minus M also. So that makes B as the most basic, then A, then C. This will be the basic character. Next, check out this 13th case. When you have OH, okay, in the case of OH, it has been slightly, I mean, although there is a SI, although there is a ortho effect due to OH, that is very, very less contribution. So the most donating will be from para position. So para will be donating because it has more plus M. And then A, then B, then D. Okay, this will be the order. Okay. While if you have OME, because the size is slightly bulkier here, it will be slightly weaker than that of meta. So therefore, first para, then sorry, para is D now. So I'll put it as para position is C here. I'll go with that. Para is C. C, then we have A, then we have D, and then we have B. Okay, because OH is withdrawing at meta position. Okay, and while in this case, you would notice that para is greater than only aniline, which is D, para is C, and some ortho effect is observed A, and the last one is B. Okay, see the slight difference here. Okay, this A and D has slight difference. This is just a memory based, guys. So you just need to remember it. In the case of OH and OME, what will happen? Okay, both will not give you ortho effect directly. Okay, so next, check out. If you have this pyrrolidine, which is completely localized, piperidine, completely localized, and then we have pyrrole, highly delocalized, pyridine, localized, and this is also localized. Okay, in such case, the most localized one is B. This is the most localized one, correct? Right. And then A, because between A and E, this oxygen is actually withdrawing. Because of its withdrawing natures, its basic character will decrease. So then E, and then D is also localized, and C is highly delocalized. So this will be the order. Okay. Next, if you have, pyrrole, which is extremely low base, and if that is shared, that lone pair is again shared with multiple pi bonds here. So in that case, the basic character further decreases. And while pyridine will have more basic, this will have the highest basic character. So D, then C, then we have B, then A. Okay, this is the order in which you'll. Next, here this is only localized. This is localized and sp3. This is localized and sp2. And this is amidine, different form only. Amidine form is very basic, and guanidine form is extremely basic. So based on that logic, D should be greater than C, should be greater than A, greater than B. This will be the basic character. Now this is very, very important, guys. Please check it out. Now this one is amidine, no problem, no doubt. It is a good base. This is also an amidine kind, correct? This is also an amidine kind, but unfortunately, here there is only donating. But here, because of the other NH, it is slightly withdrawing. And here also it is an amidine form, but unfortunately, that is also a part of the aromatic ring. And here it is completely guanidine. So guanidine is the most basic. Then A amidine is better than B, and the least one is C. Okay, the least one is C. So please check that out. Between B and C, very important case, that due to the aromatic nature here, right, this lone pair will be more involved in this aromatic form. So it will not give will not give much of amidine nature. Next, 19th. 19th between A, B, C, D here. So this CH3 is kind of donating by plus I. This is completely withdrawing. And here it is ortho effect. So ortho effect will make it extremely less basic. So therefore, A does not have any other withdrawing groups. Then C, then B has more withdrawing groups. Okay, although there is one CH3 which is kind of donating, but it's still not enough. And last comes D. These are the cases we need to know. So learn through all these cases once again. Okay, these are all something which we discussed in GOC. If you don't recall, I mean, go through the notes once again and see what is the effects that has been happening in all these cases. Okay, most of them I have taken it from the PYQs only. Whatever that has been asked in PYQs, I have taken. Okay, right. Now let's get to the uh, properties of amines here. Okay, first I'll write the chemical properties. I forgot to write the, I forgot to send the second part of amines. Let me write down here only. Chemical reactions. Next class we'll also do physical reactions, physical properties. First is about reaction with acids. See RNH2, correct? If you have RNH2 with HX, correct? It will be in equilibrium because it is like an acid-base reaction. So we'll get this as ammonium X minus as a salt. So you will get this as a salt form with acids, correct? And this works with alkyl also and aryl also. With alkyl also as well as with aryl also. You'll have the same logic here. So you'll get this as anilinium. This is like an anilinium ion with X minus. So this is also a salt. Now this is one very interesting part what we can do here. Okay. So now if I want to get back this amine once again, you take the salt here. Simply take this salt, that is NH3 plus and NH3 plus and X minus here, and react that with NaOH. The minute you add NaOH aqueous, now again it will get back to the original form, which is aniline plus NaCl plus H2O. So simple acid base reaction. Now is the interesting part, that is, if you have this salt formation and regaining back the original molecule, I can use this for a separation of organic compounds. That is, imagine I have a toluene and I have aniline. I have aniline. Both of them are in a solution here. Our objective is to separate both of them. Okay. So first of all, what we do, we add it to the ether layer. So first you'll add it to ether. Okay. So in ethers, both will be in a dissolved form. So both will get easily dissolved. So imagine they got dissolved here. Both of them are in a dissolved form here. And now what you do, you add some amount of water here. Okay. Some amount of water, H2O. On adding H2O, you will see you will get one layer of water at the bottom here. Okay. The bottom you will see one layer here. Okay. So that means you will have this aqueous layer here. We'll be noticing some aqueous layer here like this. Okay. And then we have an ether layer on the top in which this is dissolved. Got it? These two are dissolved here. And then in this, what you can do, we can add some HCl. Now we add some dilute HCl. As soon as you are dilute HCl, this will get converted into ammonium form. Now, this is what will happen here. Interestingly, you will see that in these two layers, correct? In the first layer, that is the ether layer here. In this ether layer, you will see toluene get complete. Toluene is in a dissolved form. So you will have only toluene here like this. While in the aqueous solution now, you'll notice that the ammonium got dissolved because that has converted into a salt form. Now you'll have NH3 plus that and X minus that got dissolved, Cl minus. This is in a dissolved form. So this is in a dissolved form. So once you got dissolved form, now you can actually separate it out. Okay, correct. Now you can clearly separate this out. Okay. So what you can do, you can separate this ether layer and water layer together. I mean, separate them by maybe using density features, or you can use different techniques, solvent extraction method, or we can use distillation. By these methods, we will be able to first separate out, ether completely. Ether is being separated on one, so, in one container, and aqueous solution is separated in the other container. So now what do we left over? You can see toluene got separated here, and anilinium ion is still present in the dissolved form here. So plus and Cl minus. This is how it is present. Now again what we do, we add the ether here. On adding ether layer, correct. On adding the ether layer, so what do I get here? So we'll get something like this here. So let me just copy this part. Okay. As soon as you add this ether layer, correct, we regain this. So above we will have an ether layer here, and below we have the aqueous layer. So it is still dissolved in aqueous layer only. That is, we have ammonium chloride present. And now you add NaOH. On adding NaOH, you see this reaction will take place, and aniline will get separated. And aniline is less soluble in water. Since it is less soluble in water, now we will what we will notice here is that there is a separation happened here. Okay, that is, in this case we will see that two solutions will be separated out like this. So this is the ether form. On the other side we have aqueous form. Now what will happen? Aniline will start rising up here, and it will get dissolved in this form. And NaCl will be present here in a dissolved form, plus and minus. So these are all in dissolved form. So what happened now? So we got aniline separated and toluene separated over the reaction course. Okay. So this is how the reaction will take place. And this is the advantage that we are taking when you are reacting with acids. Okay. So if aniline or any other amine forms are present which are insoluble in water, we can always use this for our advantage and convert them into a soluble salts. And then after we can do the separation process. Everybody clear on that? So this is the first set of reaction. Check out the second reaction. The second important reactions of amine includes acylation. Acylation is when you take RNH2 and react this with R dash C double bond OCl, or in the presence of or anhydride. I can take acid chloride or anhydride. Okay. In that case, what you will get is RNH C double bond O and R dash. So an amide form will form. An amide form plus Cl minus. Correct. So you can use acid chloride, or you can use an ester also. You can use an ester also, which is RNH C double bond O R dash plus ETO minus, or we can also use an anhydride. These are all acid derivatives, so they react quite easily. Some R dash. So we'll get RNH C double bond O R dash, and here we'll get this as R dash CO minus. So this way you can get acetylation done. And this is not just for alkyl, you can have an aryl group also, which we kind of learned just now. So if you have CH3O twice O, this is acetic anhydride. So that will react easily to get this as NH C double bond O CH3, and here you will get this as CH3 COOH. Correct. So here, in fact, there is H plus also. I'm just not writing it. So this is also H plus plus. So this is acetylation. Got it? Now, since there is an acetyl which has been used, this is called acylation, acetylation, sorry, acetylation. What if I use benzene for that matter? Suppose if you have same reactant here, so that is if I have aniline here, NH2, and then I have PHC double bond O Cl. Okay. In that case, we will have NH connected to C double bond O and pH, got it, with HCl. So because we are putting a benzyl group, so this is called as, okay, benzoylization. Okay, benzoylation, sorry, benzoylation. It's called benzoylation. Yes, the second reaction is clear. Right, guys. Okay, so we'll stop it here.